exponentials would be earthquakes, loudness, and we'll even look a little bit at pH. But before we do that, we're going to review logarithms. So what I'd like you to do right now is I'd like you to pause the video, and I want you to see if you can find the solutions for each of these logarithmic equations. Okay, and then press play. All I'm going to do is I'm actually going to write the answers. Okay, so go ahead, see if you can figure the solutions out for x for each of these 4 equations. Okay, so now hopefully you've pressed play. I'm going to write the solutions out. I will not show you how to do all of them just because of time's sake. So if there's one that you're not sure about, feel free to send me a message and I can go through it with you in a little more detail. So the first solution you should have got is negative 18 over 21. Okay. Now, another thing whenever I'm dealing with equations, another way to double check is you can graph this. Okay, so if you were to graph this, you would find there's no solution on the graph, and that's because this negative 18 over 21 is an extraneous root, right? We know it's an extraneous root because if we were to substitute it into one of these arguments, we'd end up with a negative solution, a negative argument. We can't have negative arguments when it comes, or negative bases when it comes to logarithms. All right, so in the next question here, your solution should be x equals 4 over 3, which is also an extraneous root. So really, we've ended up with 2 different problems that gave us an extraneous root, which means because they're extraneous roots, there's no solution for equation 1, and there's no solution for equation 2. Okay, the next question, if you were to solve this algebraically and then again double check it graphically, you actually end up with both of these being solutions. So that means here you have 2 solutions. And you may say, well, isn't the negative 3 an extraneous root? No, because if you substitute the negative 3 back into this argument, type it in your calculator, you'd end up with a positive argument. So therefore, it's not an extraneous root. Neither of these solutions are, which means we have 2 solutions. All right, the next one, if you were to show it all algebraically, you'd end up with x equals 5 as a solution and x equals negative 2 as an extraneous root. So this has 1 solution, which is 5, and the negative 2 is an extraneous root because if we substitute it back into the argument, we end up with a negative argument. So which one doesn't belong? Really, you could argue a few different things. You could say this one doesn't belong because it has 2 solutions and because it does not have an extraneous root. So maybe you say it doesn't belong because it doesn't have an extraneous root. Or you could say even this last one doesn't belong because it's the only question that has 1 solution. So it's a little open-ended as long as you're using math to verify or to back up, your answer. Okay, so now we're going to move into this next lesson here. This is another little review, I guess. This is an old diploma question. You're going to review some log laws here. So it says a student works to simplify an equation. Which step did they make a mistake in and correct the mistake? So I'm going to start using my log laws here. So whenever we have coefficients, we can rewrite that coefficient as an exponent on our argument. And remember, that coefficient only applies to the exponent on the argument. Okay, so here I have an exponent of 3. And an exponent of 4. So now I'll use exponent laws because I have an exponent raised to another exponent. I'm just going to multiply those exponents. Okay, and then from there I'll use log laws. So remember, when we have a positive logarithm, the argument will go in my numerator. When I have a negative, the argument will go in the denominator. So from here I can use exponent laws. They love to give you questions on the diploma where you use log laws and exponent laws. Very common. Okay, so when we multiply 2 exponents with the same base, we add the exponents. When we divide two exponents with the same base, we subtract the exponents. So we end up with x to the 14th as our solution. So that means they obviously made a mistake in step 3. Okay, so now we're going to look at the Richter scale and how to solve earthquake type of questions. So, how many times more intense was the 1960 earthquake in Chile with a magnitude of 9.5 than the 2005 earthquake in Chile with a magnitude of 7.8? Answer to the nearest whole number. Okay, so if we want to figure out how much more intense one thing is over another, we divide them, right? Like if you wanted to figure out how many times greater is 10 by 2, you would divide 10 by 2. Well, the same holds true with magnitudes of the earthquake. So, our first earthquake, okay, and a lot of times actually they would just give you this equation. The intensity is 10 to the power of the magnitude. Okay, so our first earthquake has a magnitude of 9.5. So 10 to the 9.5 represents the intensity of the first earthquake. The second earthquake has an intensity of 7.8. There we go. So you could type this in your calculator and that would be absolutely fine. You could also use exponent laws to simplify this. When we divide two exponents with the same base, we subtract those exponents. And we end up with an intensity of 50 times. So the 9.5 earthquake is 50 times more intense than the 7.8 earthquake. And actually, we're going to jump around a bit. So I want you to jump to the last question here, because this is another earthquake question. See, this is the formula they would give you on the diploma. And they'll always give it to you on the question. You'll never have to memorize it. The IO represents reference, so really I just kind of ignore it or treat it as 1. Okay, so we have an earthquake intensity is given by the intensity times the reference intensity times 10 to the exponent of the magnitude, where IO is the reference intensity and M is the magnitude. So an earthquake measuring 5.3 on the Richter scale is 125 times more intense than a second earthquake. All right, so what we're going to do is we're going to take our first earthquake, which is 10 to the exponent of 5.3, and divide by the second earthquake, which we don't know. That's what we're trying to find the magnitude of. But we know that the 5.3 earthquake is 125 times more intense. Okay, so we know we're looking for the smaller earthquake, so our number here should be smaller. And then from here, I'd use exponent laws and subtract these two exponents. Okay, and then I would solve this algebraically by converting to a logarithm. So my base would be 10, so I actually don't need to write that. You can if you want to. And it all equals your exponent, which is 5.3 minus m. So now from here, I'm going to type this in my calculator. So I'm going to type log 125 in my calculator. And I end up with 2.09691. Okay, and now I'll solve for m by subtracting that 5.3, the 2.09 from the 5.3, and I end up with an answer of 3.2 as my answer. Okay, so the magnitude of that second earthquake is 3.2 if I round to the nearest tenth. So, oh, I guess I could have done this one before we skipped to the last one. I forgot there was another earthquake question. We'll do this one though. A major earthquake of magnitude 7.5 is 375 times as intense as a minor earthquake. Find the magnitude to the nearest tenth of the minor earthquake. So, we know that they're given the big earthquake, and we're looking for the smaller earthquake. And the bigger earthquake is 375 times more intense. So I'm going to subtract those exponents and solve for m by doing a little bit of algebra. I'm going to convert to a logarithm. My base is 10, my argument is 375. If I type log 375 in my calculator, I'd end up with 2.57403. And then I'll solve for x by just subtracting that 7.5 to the 2.57403. And I end up with a magnitude of 4.9. So those are the earthquake questions. Pretty easy stuff. Try it out, see if you can figure it out. Now we're going to look at comparing loudness of sound. So how many times more intense is the sound of a piano playing 67 decibels than a whisper? All right. So once again, when you look at this formula, that IO represents the reference intensity. So you can think of it as 1. You could also even just ignore it. Okay, so our piano, we're going to write an equation for our piano, would be 67 equals 10 to the log I. So then I would divide that 10 over, and I'd end up with 6.7. So let me write that again. 6.7 equals log I, and then to find that intensity, the intensity would just be 10, right, because it'd have a base of 10 to the exponent of 6.7. So now I can do the same thing for the whisper. So my whisper, 22 equals 10 log I. I'll divide that 10 over. So my intensity is 10 to the exponent of 2.2. And now to figure out how much more intense the piano is than the whisper, I'm just going to divide them, just like I did with earthquakes, right? If we want to figure out how much bigger one thing is over the other. You can type that in your calculator just like that. You could also simplify it first. Either is fine. And you should end up with an answer of 31,622 times as intense. Oops, and there's our answer. Okay, so for pH, this one you may have seen in chemistry before. So the pH of a solution is defined as pH equals negative log a hydrogen ion concentration. A patient gave a urine sample which was found to have a pH of 5.7. What was the hydrogen ion concentration? So pretty easy, we're really just plugging this into the formula. Okay, so my pH is 5.7. And I'm trying to find the hydrogen ion concentration. So I would start by isolating that logarithm just like we always do. So I'd move the negative over to isolate the logarithm. Now that the logarithm is isolated, I'll convert to exponential form to find that hydrogen ion concentration. So my base is 10, right? Because we don't have a base there. It's a common logarithm, so the base has to be 10. So my hydrogen ion concentration is 10 to the exponent of negative 5.7. And you can leave it like that if you want. You could type it in your calculator as well. If you type that in, you'd end up with scientific notation 1.995 times 10 to the negative 6 moles per liter. All right, and that is our solution.